let's have a look what it means to have stationary invariance time series. So what this relates to is the concept of homoscedasticity from the regular regression line. When we speak about stationary invariance, it means the variation of that variable across time must be stationary, must stay around a constant value. So for instance, we have here the two variables, the sales and the inventory across time. Let's see which one is stationary, which one is not, and why this is going to be a problem for our regression in the time series model. So let's say this is going to be the sales across time. What we can see is that it's going to fluctuate around a certain value. Let's call that again our $10,000 worth of sale of jeans. Now, the variation around this line happens to be uniformly distributed up and down. So sometimes we're above the line, sometimes we're below the line, but in a constant manner. There is no pattern that beyond a certain value the variation increases or decreases. So here we do have a constant variance. But let's have a look here at the other one, at the inventory. Let's say that here we also fluctuate around a certain value. Let's put that value for the inventory to be equal to $4,000. That's the average value. And our time series fluctuates around it, so it reverses to the mean, so to speak, in the long run, but it reverses there in a different way. Over here we have more or less of a constant variance, but beyond this point the variance starts to increase, and let's see why that's going to be a problem. So let's say in the beginning, when the variance is constant for both variables, the way we would like it to be, we have a relationship between the sales and the inventory somewhere around at a magnitude level of 2.5, meaning that the values at a certain point in time, let's give some numbers to make it more practical. Let's say this is year, again, what did we say, 2013 or so. This is year 2013. Over here, the value of inventory is going to be 2.5 times less than the value of the sales on average. It's not going to be always like that in every year, but most of the time it is going to be this relationship. So on estimate, on average, the sales across time is going to be approximately 2.5 more than the values of inventory. This is for this time frame where we have this constant variance. So that's cool, but look what happens beyond this time. Let's say we're moving beyond year 2017. Over there, the variation of the inventory becomes higher. So in some points in time, like here, we go in this year, right? That would be, let's say, year 2020. Over here, the relationship between the inventory and the sales, for instance, it would still be 2.5, so the sales would be 2.5 higher than the inventory, but we go to a different point in time. Let me change colors for that. Let's say over here somewhere, over here, that would be year 2022, for instance. Well, look, the relationship is much smaller. The magnitude factor is much smaller. Sales is going to be only, for instance, 1.1 times bigger than inventory at that specific point in time. We go in the next year, that magnitude factor increases again to, for instance, 2.6, but then it decreases again over here. So what we're having a fluctuation in that relationship. So the slope coefficient between inventory and sales is not going to be constant across time. That's the definition of not a stationary variance. We can see that the variance is going to keep increasing. So because the variance keeps increasing, the relationship between the inventory with sales across time will change. So we cannot predict a constant slope coefficient. That's why if this does not hold, that the variances are both constant for each independent and dependent variable, then we are not going to have stationary invariance time series, so that we cannot predict a time series regression model. That's why this is a necessary condition. Hope this proves the point. In the next video, we're going to look at the stationary in covariance assumption.